And good afternoon, everyone, and welcome to this presentation. My name is Alejandro Perdomo Ortiz, and I'm the Associate Director of Quantum AI at Zapata Computing. During the last 14 years, I've been working on the development and implementation of quantum algorithms to solve real-world problems, in particular in the domains of optimization and machine learning. At Zapata, we build software for quantum computers. We build custom quantum algorithms for applications across many industries, including optimization and logistics, materials discovery, and statistical modeling in finance. We have also built a platform called Orquestra, which I'll share with you today. We built Orquestra first for ourselves because we couldn't find anything out there which was extensible, modular, and scalable enough to tackle and to build the complex hybrid quantum classical algorithms required to solve real business use cases. In this presentation today, I will tell you how we use Orquestra to deploy a new quantum algorithm that we built at Zapata that pushes the limit of quantum machine learning with near-term devices, quantum devices. So more specifically, the context of the machine learning task is in the case of generative modeling, and I will show you how we can generate images with a quantum computer. So generative modeling is one of the most complex tasks in machine learning. In particular, you might have seen actually these images, but I invite you to check this website if you are not familiar with the deep and profound successes of generative models. For example, if you go to this website, thispersondoesnotexist.com, you will see actually that all these human faces actually were generated by a machine learning algorithm. In particular, by one of the frameworks that is called the Generative Adversarial Network. There was actually a nice, a recent post by the New York Times featuring this website, where you can find, for example, that you can buy or request even a package of 1,000 fake faces, for example, for your new movie or your new video game. So now, taking it one step down, you find actually the canonical data set that every single machine learning expert in the community uses to benchmark their algorithms. So the data set is called the MNIST, and it consists of 60,000 digit images of handwritten digits. So in the MNIST data set, the task is the following. I'm giving you these images that we call the training set, and you're supposed to come up with an algorithm that generates images just like those ones. Just to give you an idea, the task is far from easy with quantum devices. And this is what you find, for example, when we think of NIST devices, gate-based devices. This is actually the state of the art. This was published in October 2020, and this is actually the best and the high quality digits that you can get out of a quantum computer. This is actually the images on the top that you see are the ones corresponding with a 0. And with some imagination, you can see actually that the ones at the bottom correspond to number ones. So that's the best that we can do at the moment with gate-based devices. Now, the question that we asked and the context of what I'll be showing today is to show you actually a positive answer to this question is, can we enhance generative adversarial networks with quantum models running on these devices? So let's take a closer look to the generative adversarial networks. So there are actually 4 main components inside a GAN. The first one is the generator, that is the one responsible for generating the images. That's basically the core of your machine learning algorithm. There is as well as a prior that is a probability distribution in most of the designs, just noise, that actually it will be just giving you the diversity that you need to generate new images. So when you sample from the prior, at the beginning of the training, the outcome as well is also noise. Now, the task of the discriminator is just to make sure that the that the images that it classifies as fake, the images coming from the generator, but it would classify as true the images coming from the data set. In this adversarial game of actually the discriminator playing the role of trying to tell apart which ones are fake and which ones are true, the generator gets better and better at generating images, as you can see here. So as the training progresses, then the generator actually can become really good at generating handwritten digits in this specific case. Let's take actually a closer look to some of the components in such a way that we can frame the associative adversarial network, which is a variant of the GAN. So when we look at the prior, in the proposals for the prior, as I mentioned, this is usually a uniform probability distribution, as can be depicted by these points thrown at random, and then the generator just kind of turns this into real digits. Now, when we look at the discriminator, there is also a component at the end of the discriminator. Both the discriminator and the generator are deep neural networks that perform this task. So they're actually classical components. The latent space that we called is the layer just right before it makes the classification. And one of the key observations is that the latent space, as well as the prior, has a dimensionality that is much smaller than the dimensionality of the data itself. Now, the observation in the transition between the GAN and the associative adversarial network is the realization that when the real data comes in through the discriminator, notice that the one is ticked, so that basically that's the real data coming from the training set. The latent space actually is far from being completely random, as it is in the case of the prior. So the idea in going from the associative adversarial network is this realization that there is a lot of structure in the latent space, and that it would be great if the prior is in some way mirroring the latent space that you have on the right-hand side on the discriminator. By doing this game and keeping track of the latent space of the discriminator, hopefully the expectation is that the generator as well is getting better and actually generating better images because it's sampling more efficiently from this structured space. Now, what we're going to be discussing today actually is that this is a great opportunity for quantum computers because of the reduced dimensionality of the latent space and the prior. And this is actually where quantum computers can come in, and small quantum devices in particular. Now, in the work actually that we published recently in the archive, is we proposed a new framework that is called the Quantum Circuit Associative Adversarial Network, or QC-AAN. And basically, in a nutshell, it is a hybrid quantum machine learning approach for large-scale data sets with NIST devices. So you're already familiar with from the picture, you're already familiar with the generator and the discriminator. I notice actually that we are inserting, just replacing as the quantum component, just replacing the prior of the network. As I mentioned, this idea of working with the reduced dimensionality space is an idea that we proposed about 3 years ago. And that's basically is the best way to work and to cope with the limitations of these NICS devices that are very small in scale. Specifically for this implementation, we needed to model this probability distribution in the prior. So we used a model that we proposed about 2 years ago called the quantum circuit board machine. So the quantum circuit board machine, in a nutshell, is a quantum circuit framework to load arbitrary probability distributions into the wave function of a quantum device. So that was tailored to solve generative modeling tasks and to solve any probabilistic modeling task in principle. Now, as another extension actually of our work, we propose here a novel approach that leverages on the unique quantum resources that you can find when you measure in bases other than the computational basis. As I'm showing here in this cartoon on the left, what you see is, for example, we're not only collecting samples in the computational basis, but we're enhancing the power and the expressibility of the probabilistic model, but also including measurements in the orthogonal basis, like in the Y basis, or also, for example, one of the things that we did also experimentally as well is that you can even let the entire hybrid quantum classical algorithm to decide which bases you should measure. And that's the power of this approach. Now, let's see actually how we implemented this complex model utilizing Orquestra. So in theory, everything is nice and simple. As I told you, you have usually 4 components, and that's how it looks from a very high level view. You have a GAN, you have a prior, you need to run the training set, and you need to specify some of the details. But as we know, when you're doing software development and integrating all these models, in practice, each one of these components could be very complex, but it's modular in approach. So this is actually when Orquestra comes and can help you the most. So how is actually Orquestra helping you in this task? So first of all, it is keeping track of the many parameters that you have in your workflow, in your pipeline. So second, it gives you a lot of algorithm flexibility because, for example, as we are showing here, we are able to stitch classical and quantum components together very seamlessly without actually, you don't have to worry about the connection between them or the incompatibilities between these models. So of course, you need to design them, but basically once they're there, you can actually easily swap information between these components, classical and quantum, as we did in our experiments. And the last point actually related to something unique in Orquestra, that is the containerization. Orquestra is built based on Kubernetes as part of the workflow management system. And what that allows you to do is to isolate resource allocations in such a way that you can manage, Orquestra is managing for you the complex dependencies in such a way that, for example, you don't need to worry that's usually the concern when you're working with Jupyter notebooks about not having the right version of Python or TensorFlow. So all these complex dependencies are taken care for you. Finally, it allows you as well, this containerization and the fact that everybody will be running the same experiments, it allows you for reproducibility and to parallelize at scale. So you can share actually your workflows with your colleagues across the globe, and they will be able to run the same experiments that you did. Let's see actually in action some of these different features. So as we mentioned, the core of our hybrid quantum machine learning algorithm is the quantum prior. So we are taking from the diagram from the right, we're only isolating the decision of actually working and fine-tuning the quantum prior. Specifically, for this particular experiment that I'm going to show you, and this is actually going to be available in Orquestra, as you can see on the right, you can run the uniform prior, that's what we discussed at the beginning, that will lead you to a GAN. Or you can run actually with a restricted Boltzmann machine. That would be the case of the Associative Adversarial network. Or you can run the QCBM, the quantum sequence Born machine, and even the enhanced QCBM with the multi-basis technique that we proposed. And it would only take actually to change a few lines of code to recycle some of these features that we already implemented in Orquestra. Of course, you will need to define the specifications of each one of the priors that you choose. But for example, in the case of quantum circuits, you will need to specify the number of qubits, the number of layers that you want to have, and that's what you define at the top of the workflow. But it's just a matter of actually editing the workflow in order to give this a go. Now, let's actually, another possibility that you can have in Orquestra is actually the possibility of swapping from one backend to another. What you see here is, for example, that just by changing 2 lines of code, you can swap from actually doing your runs on the forest simulator. That's the one that we chose for running the circuits, for simulating the circuits. But then also, for example, you can actually, just by changing 2 lines of code, you can swap to an IonQ. And instead of getting the simulations in silico, you might get the runs directly from hardware. And why not, for example, another backend that you might like to try is you might want to run this in Honeywell. And again, it will take you only actually to change 2 lines of code in your workflow. So this is just actually even details of the prior that you can swap very, very easily and conveniently. Now, actually, one of the power of Orquestra, as I mentioned, is the orchestration. Orquestra is actually the orchestration capabilities. And why not actually to run all the experiments that you want to run in one shot? As I'm mentioning here, for example, you can run actually directly in Forest, do simulations, and actually go with the IonQ backend and also with the Honeywell backend. And also, this is just a handful of the ones that you might like to try. For example, we can run in superconducting qubits just by running, for example, IBM's quantum computer or Rigetti's quantum computer, and you can have we will have some more offerings coming up soon. Also, in terms of quantum simulators, you can actually have Circ, IBM Qiskit, QHipster, so many other backends that we usually do and try as quantum scientists. Now, if you want to check the results on the Honeywell experiment, so don't miss the talk tomorrow, the Honeywell's talk tomorrow, where our CEO, Christopher Savoy, will be speaking with Tony Utley, the president of Honeywell's Quantum Solutions. Another neat feature of Orquestrate is that you don't have to worry about the progress of your results. It will actually keep track of every single aspect from the classical simulations to the quantum simulations, and you can just check the status as they are finishing. Now, let's actually take a look at the results, at the final results, in generating these high-resolution images. So in the y-axis, what you see is the inception score. The inception score is telling you about the quality and the diversity of the handwritten digits. The higher the inception score, the better the digits that you're generating out of the hybrid quantum model. On the x-axis is the epochs, and that's basically tracking the evolution of the generative model, of the hybrid, of the training of the machine learning model. And the 5 lines that you see here is all the runs that we did in Orquestra, as I mentioned, in an Orquestra in an orchestrated fashion, where actually you can have the black squares that corresponds to the classical simulations. You have the triangles, the blue triangles that corresponds to the simulations of the quantum experiments, and the hexagons correspond to to the experiments on real hardware from this all end-to-end implementation. Now, at the beginning of the training, the digits they look very blurry. So as we move through the epochs, but as the algorithm progresses, you see that the algorithm is getting better and better at generating the digits. And as you can see, when you reach all the way to the end, the best result that you get at the end of the training is something that resembles the training data set that I show you, the MNIST data set. So really high resolution digits. So one of the things, I invite you to check the details in the paper, but what we show here, even in this experiment, is that when you do the benchmark against comparable GANs, we see that there is a quantum enhancement by using this hybrid model compared to just the purely classical approach. And also it stabilizes the model even more significantly than when you have just the entirely classical model. So I invite you to check the results there. So I hope, with this, I convince you that this is a big step forward, to working with complex and full-scale data sets in machine learning, and that we're certainly excited about the opportunities and the potential of using near-term devices in this complex generative modeling task. So I would like to wrap up by inviting you to join the Quantum Revolution. So check out our website, Orquestra.io, for documentations, tutorials. For example, there is a tutorial about the QC-VM. The QC-VM, as I mentioned, is a model that has been implemented in 5 different hardware providers. So you can check some of the tutorials, the machine learning tutorials, and there will be more demos coming up. And also check our zapatacomputing.com/research for more news about the developments. In particular, there was one development that I didn't have a chance to speak about, that is this quantum enhanced optimization, where we show that we're using quantum-inspired models to boost the performance of classical solvers. As you can see in Orquestra, you can find many different backends and many different open source tools that I'm pretty sure they will be valuable for your research and for all your developments in the industry, as you attempt to use these near-term devices for real-world applications. So if you have any questions, please don't hesitate to reach out to us, and thank you for the attention.